Comparison between substitution and elimination reactions. Both are important class of organic reaction which we frequently encounter in our organic chemistry course. So today we will focus on this reaction with respect to different factors by comparing them with one another. So let's first focus on, we have studied two different type of substitution reaction and two different type of elimination reaction. In substitution, we have studied SN1 and SN2, and in elimination reaction we have studied E1 and E2 mechanism. So let first, this is first order kinetic, and this is second order kinetics. Similarly, E1 is first order kinetics, and E2 is second order kinetics. In other words, we can say that both SN1 and E1 they are unimolecular, or their kinetics rate is equal to the concentration of substrate. And as far as SN2 and E2 are concerned, they are bimolecular, and their kinetics rate depend upon the concentration of substrate and base nucleophile, base in elimination reaction and nucleophile in substitution reaction. So this simple demonstration, let's first focus on the mechanism. SN1, which is, let's consider a reaction, a tertiary butyl bromide give a tertiary butyl alcohol in SN1 fashion. Similarly, an E1 mechanism, here we have chloride and this is hydrogen, and we react it in the presence of methanol, we get alkene. Usually in elimination reaction, whether they are E1 or E2, so we get alkene, which is a sound identity for elimination reaction. So SN1 is a three-step mechanism. Step 1 involves a slow ionization of substrate for generating a carbocation. Step 2 involve nucleophilic take on the carbocation, and in step 3 deprotonation give the final product of tertiary butyl alcohol. So this is a three-step mechanism. As far as E1 is concerned, it proceeds through two steps. Step 1 involves the ionization of substrate, which is reversible like SN1, for generating a carbocation. And in step 2, this is step first. In step 2, beta proton is abstracted by the base, which is methanol in this case. And we get the product alkene. So in both cases, the first step is slow, which involves the ionization of substrate. So this first step is rate determining. So in both cases, step number first is rate determining step, where only a single molecule of substrate is involved. Therefore, that's why we call both SN1 and E1 as unimolecular, or their kinetic depend upon the concentration of substrate alone. As far as SN2 is concerned, it is single step mechanism in which a nucleophile take a substrate in a single step for getting a substitution product, which is ether in this case. So this is single step or concerted, in which the nucleophile approach or attack from the back side on the carbon atom bearing the leaving group. And as far as E2 is concerned, that is also concerted and single step mechanism, in which a strong base is required for abstracting a beta proton. Here we have a leaving group, and we get a product of alkene. So this is all about SN2 and E2 mechanism, which both are single step mechanism, and they are bimolecular in character. So their kinetics depend upon the concentration of both substrate and base nucleophile. Remember that we talk about nucleophilicity in case of substitution reaction and basicity in case of elimination reaction. Nucleophilicity is a tendency for making a bond with the carbon atom bearing a leaving group. With carbon atom, which we usually observe in substitution reaction. And as far as basicity is concerned, it reflects a likelihood or tendency for abstracting a beta proton. Abstracting a beta proton. So we talk about nucleophilicity in substitution reaction and basicity in elimination reaction. Substitution reaction and basicity in elimination reaction. Now let's consider different factors that relate each of these mechanisms with each other. So let's first focus on different factors. Factor influencing substitution and elimination reaction. Let's first consider substrate. As SN1 is concerned, so both in SN1 and E1 we get a carbocation. In SN1 the carbocation is attacked by the nucleophile both from the above and below the plane. Therefore the starting substrate should be the one that gives rise to formation of a stable carbocation. So the rate of both SN1 and E2 mechanism where carbocation is formed usually take place at faster rate in tertiary alkyl halide than the secondary and in primary. And as far as the SN2 and E2 are concerned, in SN2 we usually require a less bulky substrate such as primary alkyl halide. In primary alkyl halide the SN2 reaction takes place faster than secondary alkyl halide. In tertiary alkyl halide we do not observe any SN2 reaction. As far as E2 is concerned, in E2 usually we get, whether both E1 or E2 we get alkene. So if the alkene are highly substituted, then they will be stable, and only the substrate that give rise to a stable and substituted alkene will promote a faster elimination reaction. So its order remain the same. So for both E1 and E2 the order is same with respect to substrate, but in SN1 and SN2 the order is reverse. The second factor is solvent. Both for SN1 and E1 where the first step is slow and require ionization of substrate, therefore polar protic solvent promote both SN1 and E2 mechanism. Polar protic solvent include such as methanol and water. And as far as SN2 and E2 are concerned, we usually require a strong nucleophile for E2 and a strong base for E2 and strong nucleophile for SN2, and there is no need for a solvent polarity. The third factor is nucleophilicity. And basicity. Usually base is required in elimination reaction, whether it is E1 or E2. Usually a strong base is required for promoting E2 elimination reaction, but there is no such requirement for E1 elimination reaction. And as far as nucleophilicity is concerned, it usually tells us a relationship for making a bond with the carbon atom. So we talk about nucleophilicity in substitution reaction. So we have two types of substitution reaction, SN1 and SN2. In SN1 there is no need for stronger nucleophile, but SN2, which involve a backside attack for expelling the leaving group, require a strong nucleophile. The fourth factor is stereochemistry. As both SN1 and E1 lead to formation of a carbocation which is planar in character. Therefore, the stereochemistry of starting material is not important. As far as SN1 is concerned, the carbocation can be attacked from both above and below the plane, and we get racemic mixture with a slight proportion of greater inversion than retention because of ion pairs. But as far as E1 is concerned, it usually gives a substituted alkene or ZCU product. In greater proportion as compared to Hoffman product, which give a less substituted alkene. And as far as SN2 is concerned, the stereochemistry is inverted, or inversion is observed in SN2 reaction. If we have a starting material of R configuration, then we will get a product of S configuration. Similarly, in E2, we require anti-periplanar conformation, and both the leaving group and proton or beta proton should be in anti-periplanar conformation for facilitating a fast SN2 reaction. And as far as kinetic is concerned, both SN1 and E1 are unimolecular, where SN2 and E2 are bimolecular reaction. The fifth factor is rearrangement. As both SN1 and E1 involve the formation of carbocation, therefore both reactions are prone to rearrangement. So rearrangement is observed in SN1 and E1. But as far as SN2 and E2 are concerned, they are single step mechanism, so there is no rearrangement. The sixth factor is orientation. Usually we talk about the position of a double bond. For example, if we have alkene or alkyl halide in this conformation, we get two stereoisomers. One is tri-substituted and another is di-substituted. This is ZQ product and this is Hoffman. Usually ZQ product form in major proportion because it reflects a stable alkene. So this is elimination reaction. Usually this is a question of regioselectivity, which tells where the double bond will form. So at this position the double bond will preferentially form because it gave the stable tri-substituted or ZQ product in major proportion. Similarly, SN1 and E1 stereochemistry is not important because in SN1 we get racemic mixture and E1 give us a ZCU product. As far as SN2 is concerned, it is stereospecific because we get only one stereoisomer in the product, and as far as E2 is concerned, it is regioselective, stereoselective and stereospecific. From regioselectivity we means where the double bond will form. Just both E1 and E2 are regioselective because we get a highly substituted alkene. As far as stereoselectivity is concerned, it tells us about the formation of different stereoisomers such as cis and trans in E2 elimination reaction. And similarly, in stereospecific reaction, we get only one stereoisomer. So both E2 and SN2 are stereospecific reaction. So this is all about a substitution and elimination reaction. We should have a clear idea about mechanism first. Once we have a clear idea about mechanism, then definitely we can easily correlate them along the different factors which we have studied right over here. As far as SN1 is concerned, it is a unimolecular elimination reaction that proceeds through 3 different steps: 1, 2 and 3. Similarly, E1 mechanism also proceeds through 2 steps. Here we observe the formation of carbocation both in SN1 and E1. Carbocation is formed. The first step is slow, which is a rate determining step. As far as SN2 and E2 are concerned, they are single step mechanism. We call them concerted. This is also concerted. So both mechanisms proceed through single step mechanism. They are bimolecular in character, and their kinetic depend upon the concentration of both base and substrate. We have studied different factors such as substrate. For SN1 we require this order. For E1 we also require the same order. For E2 we require the same order, and for SN2 we require opposite order. As far as solvent is concerned, good ionizing solvent is required for promoting both SN1 and E1 reaction. And as far as SN2 and E2 are concerned, so no need of good solvent. As far as nucleophilicity and basicity is concerned, nucleophilicity, we talk about nucleophilicity in substitution reaction, which reflect a tendency for making a bond with a carbon atom bearing a leaving group. And as far as basicity is a phenomena which concerned with abstraction of beta proton. Stereochemistry in both SN1 and E1, there is involvement of carbocation formation, so we get racemic mixture for SN1 and ZCU product for E1. And as far as E2 are concerned, both in E2 we need anti-periplanar conformation. Rearrangement takes place in SN1 and E1, so no rearrangement takes place in SN2 and E2. And as far as orientation is concerned, we usually get highly substituted alkene in elimination reaction. And as far as orientation with respect to SN2 is concerned, so we get inversion of configuration. So both SN1 and SN2 stereochemistry is less important as compared to SN2 and E2, where SN2 is stereospecific reaction and E2 is regioselective, stereoselective and stereospecific. E1 is also regioselective as well because it tells us about where the double bond will form. Thank you for watching the video.